Hello everyone, welcome to this material characterization online course organized by NPTEL. In last two classes, we have been looking at optical metallography or microscopy in the form of a tutorial classes. I would like to continue this same thing. Today, I would like to introduce some of the statistical methods with which we will be able to do some quantitative metallography which I demonstrated in the last few classes. So, I will straight away start with the these methods. Okay. We have to now just look at why do we need this statistical methods. For example, what I have just written here is to handle all aspects of analysis of data obtained by random sampling. So, what does it mean? For example, in the quantitative metallography, what we have just discussed in the last class, for example, if you want to calculate the volume fraction of the second phase or a particle fraction in a matrix, or if you want to just measure the particle size or the grain size and so on. So, you do the sampling in a random manner. So, any data which you obtain in a random sampling, for example, I mentioned that you have to do the sampling with the several micrographs, whether you use it any probe, whether it is a grid or a mesh or so on. So, we will just look at the actual examples when I go to the next class, but I will just briefly mention what are all the mathematical tools which are required to have the statistical analysis. So, that is the idea of this tutorial class. So, first one which comes in that category is mean and standard deviation. You all must have heard about this mathematical terms in your previous classes, but then why we do apply these methods here is how to represent the data which you obtain from the metallographic measurements to get a quantitative information about microstructure. So, that is our primary aim. So, unless you have this background, so you will not appreciate when we actually go and work out the examples. That is why I am just introducing this statistical methods briefly. So, what is mean and standard deviation? I will briefly write. So, if the measurements are made of many features in a sample, they will have variability about mean value for the sample. What does it mean? It means it is usually assumed that the values So, it is usually assumed that the values x, whatever you may be measuring for any of the metallographic parameters like or stereological parameters, x are distributed normally about the mean, that is x bar, to give a frequency f distribution. So, how to visualize this? We will, so let us try to write, that is mean x bar is sigma x divided by n, and the width of so the mean x bar is equal to sigma x by n. The width of the distribution is determined by the standard deviation s, where s square is equal to sigma x minus x bar whole square divided by n minus 1. Suppose if you, in a normal distribution, So, what I have written here, for a normal distribution, 67% of the measured values of x fall within plus or minus s of x bar, and for a 95% of confidence level will fall within plus or minus of 2s of the x bar. So, we can plot this and then we can discuss about that. So, let us plot this. What is that I am seeing? So, whatever we have just written here, we have just plotted this. So, you have the x bar, which is a maximum, which has got a distribution between plus or minus s for a 67% of confidence level. For a 95%, it falls between plus or minus 2s. So, this is how the distribution is mentioned here. So, how does this help in quantitative metallography? For example, if you want to measure the volume fraction of the second phase in a two-phase material, so you just use some of the traverse line across the micrograph, and then you just start counting the point which is intersecting, or the number of features per unit length. That also you will do random counting or random sampling, and then which can be plotted with this kind of distribution. So, the one of the strict rule is, suppose if you choose a random line for a traverse which is traversing the micrograph, and you have to make sure that no two points or intercepts will fall in the same features of the micrograph, whatever we are interested to measure. So, that is the statistical rule. We have to make sure that the traverse line, that is a random line, are well separated from the features which we are measuring. That means, you should not measure the same feature twice. So, then the random sampling is valid, and this can be represented by this simple distribution functions. So, now we will just look at the other way of distributing the data, called So, what I have written here is, suppose if you want to generate an histogram where you have the complete particle distributed in a matrix to measure the particle size and its distribution and so on. The one tedious method of doing is measure each particle accurately and then start counting and put the sizes into different classes. So, instead of doing individual particle size measurements, you fix the range, small size intervals delta x selected so that k, suppose you have k times, that is say 10 or 15, so many intervals. The intervals, number of intervals you can choose depending upon the size range you have, for example, very small size to the big size or medium size and so on. For example, if you have the 10 to 15 size intervals, which covers the full range of particle sizes which is there in the micrograph. So, you can choose that, then we can generate an histogram easily. So, what we can do is to approximate a normal distribution, something like what we have seen before. So, a histogram So, what is that we have written here? I said that instead of measuring an individual particle, we can choose a size interval delta x, and if you plot a histogram, it can be done by plotting number, that is small n, of each size group xi, where I is the values of 1 to k. It can have, for example, 10 to 15, something like that, and then you can write Fi is equal to Ni by sigma Ni, which is nothing but Ni by n. This n is the number in the each size group, that is the small n, and so the data in the form of a histogram are analyzed in the similar to what we have seen in the previous normal distribution. So, you can rewrite this mean x bar is equal to sigma Ni xi divided by sigma Ni, which is nothing but sigma Ni xi divided by small n, where xi is the midpoint of the each size interval, that is xi is equal to I minus half into delta x, this delta x, that is the size interval you have chosen, delta x is here. So, then we can rewrite the standard deviation, which is s square, like what we have written similarly, is equal to sigma Ni into x minus x bar whole square divided by sigma n minus 1, which is nothing but sigma Ni into xi minus x bar whole square divided by n minus 1, which can be recasted like this: sigma Ni xi square minus n x bar square divided by n minus 1. So, this is what you will have if you choose to select a size interval to plot a particle size distribution in a which is having a huge size range. So, how does the plot will look like? Let us plot the histogram for just for a comparison. So, this is how the histogram will be looking like. So, I have just superimposed the normal distribution curve for the easy reference, what we have done in the previous case. Here you see that x bar, and this is a random xi. So, you have the size range x1 to x k. So, you have this. So, this is the delta x size range you have chosen, and this is how your histogram will be looking like if you choose to measure a particle size in a micrograph. So, this is another technique, statistical technique. So, what we will do, the next one is the standard error and confidence limits. So, we are just looking at the next parameters, standard error and confidence limit. The mean and the standard deviation of a sample are usually determined to provide an estimate of a mean value of a population, that is in the bulk of the volume for the quantitative analysis. So, to do this, the variability of the sample mean must be determined. So, this is given by the standard error of So, we are trying to find out the variability of the sample mean. So, and this is given by the standard error of the sample mean, that is S into x bar, which is related to the standard deviation like this. So, standard error, that is S x bar, is equal to small s, which is standard deviation, divided by square root of small n. So, what I have written here is we were talking about the sample means x bar will be distributed about mu. The sample mean itself will be distributed about mu in a t distribution. We will just I will just show you what is this t distribution, and before that we will see that the range of values in which 95% of the sample means fall is related to the standard error, the multiplying constant T 95 n minus 1, depending upon the number of measurements in the each sample or the number of degrees of freedom. So, this is what you have to realize. So, what I will now do is I will just plot the T 95 n minus 1 and you have small n. So, T 95 n minus 1 is the multiplying constant versus the number of measurements. It will be, so this is having 0 to So, what you can see is the dependence of T95 n minus 1 on the number of measurements small n. You can see that and beyond so beyond this 20 number of measurements, it remains almost 2. So, this is what this plot is illustrating. So, the standard error multiplying constant depending upon the number of measurements you make, that is small n. To illustrate that, this plot is given, and you can say that so what I have written is when the 95% confidence interval is known, and this can be applied to the single value of the mean x bar determined from the experimental sample, in order to define the range within which there is a 95% of probability that the population mean lies, which can be written like mu is equal to x bar plus or minus into T95 n minus 1 into S into x bar. This is standard error, and this is the multiplying constant, and this is the population means. So, this is how we have to look at the confidence limit. I will just continue this few more parameters, and then we will actually apply these techniques into some of the basic metallographic examples in the next tutorial class. Thank you.